In fact, indeed, it's an honor for us, and he invited us to present. In fact, it's a great time for us, and I would like to present the importance of, just let me share my thing. Is it okay? Yeah. Now the thing is, we want to present the role of tubular lead acid battery. The tubular lead acid battery for solar off-grid applications in African continent. The thing is, today we talk about energy. The energy is a buzzword across the globe. Wherever you go, people talk only about energy. So let us see why it is so. When you talk about energy, energy is an enabler for development. For example, from morning to night, every household, all the activities like cooking, heating, cooling, lighting, appliances, IT and communication technology, industries, and of course, mobility. Everywhere, they are using energy. The energy we are using, either in the form of material or in the form of electrical energy. If it is material, either it is gas or biomass, or electrical energy, we know electricity. If you look at this slide, almost all the activities, electrical energies play a very, very critical role. Now let us see how much electrical energy is on today used in African countries. This is the data which I have taken from IRENA 2021. African continent is having 1.276 billion people, and they divide into 5 continents: Northern Africa, East Africa, Central, West, and Southern Africa. 98% of Northern Africa is accessible to electricity, while 47% from East Africa, only 30 from Central Africa, 53 from West Africa, and 51 from South Africa accessible to electricity. Overall, 54% accessible to electricity and 46% not accessible to electricity. This means 568 million people do not have electricity access in African continent. Even if we talk about the electrical access, it is divided into 5 zones, like 5 categories, like 0, 1, 2, 3, 4, 5. Tier 1 means it's just for lighting and phone charging. And tier 2 means lighting, phone charging, plus TV and fan. Just like that. Now these 568 million people not accessible to electricity. The remaining people, they are accessible to electricity mostly in tier 1 and tier 2 category. Now you may ask why this electrical energy consumption is so important. Let's see in the next slide. These United Nations 2018 and 2019 data. The UN bring a concept called Human Development Index. The Human Development Index, basically it's a life expectancy and expected years in schooling and gross national income. This HDI is a mixture of these 3. If you compare the various countries like USA, Japan, Germany, China, India, and Africa, just have taken 2 countries, Kenya and Nigeria. Look at the per capita energy consumption, that's electricity consumption. Kenya consuming 205 units per person per annum, whereas Nigeria is consuming 142. America is consuming 13,000 units. China is 4,900. India 1,181. Now look at the Human Development Index column. 0.539 for Nigeria, 0.6 for Kenya, and 0.926 for US. Look at the life expectancy. Today, an African is living around 54.7 to 66.7 years. So 60 plus minus 6 years. Whereas in Japan, average life is 85 years. That means higher the electrical energy consumption per person, higher the standard of living, higher the health of the nation, higher the prosperity of the nation. That means this slide shows Africa consumes much lesser energy and they need to consume more for better life. The thing is, okay, Africa is consuming energy. Why Africa is not consuming more energy? For that, one has to generate more energy. For that, let us see what are the energy sources across the globe for generating energy. One is the renewable, second based on thermal, then hydro is a major thing, and nuclear. These are the 4 major energy sources available to generate energy. Now, what are the impacts? When you go for thermal, basically we'll be using either coal or oil. Is a non-renewable. And because of this, today across the globe, we talk about global warming and climate change. Then this thermal power plant is more of a centralized energy. That means you generate energy in a particular place and you transmit energy through various mechanisms. And during transmission, there's several losses happening. And places like India and most in Africa also, a lot of theft is happening. That means the thermal power plant, due to global warming and climate change and centralized nature, more and more countries are going away from thermal power plant. The nuclear power plant. For nuclear power plant, we need a place which is earthquake prone area. Here also it is centralized. Hydro, it's a season based. We need a huge water and landscape should be something like that. And once again, decentralized. But only thing is much cheap is solar and wind. There is no impact on environment, and it is decentralized. This kind of decentralized energy source and without having impact on global warming or climate change, these are the things developed countries should look for it. Now, based on today, how is the energy mix, energy generation mix across various countries? Say, for example, USA in 2020, they produced 4,111 billion units, out of which 21.8% coal, 38.3% say gas, solar is 12%, nuclear is 18.9%. Look at Africa, or China, or India. China and India heavily depends on coal. That's why across the globe today we talk about global warming and everything. And China and India has taken the leading in reducing the thermal power generation. Whereas in Africa, the solar is only 5% as on today. And look at how much Africa is generating energy. It's only 844 billion kilowatt hour per billion unit. Its population almost equal to Indian population, but it is producing half of what India is doing, or 1/10 of what China is doing, 1/5 of what America is doing. That means Africa is generating very low electrical energy comparing to its population. That's why Africa is not consuming more energy, and their energy mix is only 5% solar, in spite of there's an abundant solar energy. This the solar map of Africa, if you look at that, 1 square meter area per year, Africa can produce 2,410 units electricity. And in average, Africa, if you look at the entire Africa, they can produce 2,000 units per person per annum in 1 square meter. Such a huge amount of energy available. In spite of that, Africa is using only 5%. So this, the entire Africa should really think what to do next. Suppose if Africa goes for solar energy, which is going to happen anyway, it is bound to happen due to global, the environment change, global temperature rise, everything solar is a must. When you go for solar, the solar energy we are consuming in a different time and we are generating in a different time. We will be generating between morning 6 o'clock to evening 7 o'clock, peak around say 2 to 3, and we are consuming at 2 different times. That means whatever energy we are consuming, it has to be stored so that it can be used in the 2 peak times. For storage, we are having plenty of options. We can store in chemical energy. We can store in mechanical energy. We can store as an electrochemical energy, or we can store as a thermal energy. In each division, there are plenty of divisions. Say, for example, in chemical energy, it can be in the form of hydrogen, or natural gas, or chemical compounds like methanol and ammonia. In mechanical energy, it's a pumped hydro, compressed air, flywheel. Whereas an electrochemical, it can be fuel cell, or batteries, or supercapacitors, or superconducting magnets. But as per our analysis, the battery seems to be a better choice. The reason being, the energy can be stored from milliampere hour to mega ampere hour. Even you can electrify the village using the energy stored in battery. And energy efficiency, when you go through battery, it's more than 85%. And battery material is recyclable. And battery response time, it's in the form of millisecond. And life of battery, it's nearly 15 to 20 years. And it is rechargeable. It is decentralized, less pollution, minimal global warming, and of course, it is affordable. Due to these reasons, battery storage is very, very critical. When you go for a storage, there are 2 types of, when you're using solar, one is on-grid application, and there is off-grid application. An on-grid application means you take energy directly from solar, straight away give to the main grid, okay, without storage. Whereas off-grid means you take the energy from the solar, using solar, sun from solar panel, then store it in battery, and this battery energy can be stored whenever you want it. But even nowadays, even the on-grid application, people started using battery. That is for quality of the power. Say, for example, in Western countries like USA and Europe, they're full of power, they're having rich of energy, but they need a quality power. The quality power means it is used in frequency regulation service, load following services, peak power shaving, energy storage. In these 4 areas, the solar on-grid, people started using battery. But in the African continent, we need for off-grid application. When I say off-grid application, what are the areas? One is the remote area power supply. See, there's a remote village. We may not be having a power. There, using a battery, only solar and battery, remote area can be electrified. And village can be electrified. Agriculture pump, residential lighting, vegetable vendors, even market in the evening, and cold storage facilities, because there are several, vegetables, in fact, decay in the absence of cold storage facilities. Their battery can be used. Primary health center for vaccine storage system, and remote area telecom tower. And these are the areas where off-grid combination with battery can be used. After knowing the importance of battery, just I want to touch what is a battery. It's an electrochemical power source where a chemical energy comes into electrical energy. That means the energy of the reactant and energy of the product This difference manifested as electrical energy when chemical reaction takes place. And in electrochemical cell or in battery, this efficiency is nearly 100%. That's why battery, what we call is a perpetual machine. We are having a plenty of battery, a secondary rechargeable battery, that's lead acid, nickel cadmium, nickel metal hydride, nickel zinc, it's alkaline battery, and lithium ion battery, sodium ion battery, this is another battery, and flow battery, high temperature, metal air battery, fuel cell. Yes, and today lead acid battery is extensively used, and lithium ion battery, it started appearing everywhere. Now, this is the thing, lead acid and lithium ion. Lead acid is only one type, the chemical reaction only one. Whereas in lithium, there are, yes, and today there are 4 types of battery. One is lithium cobalt oxide, but called LCO. The nickel manganese cobalt oxide battery, NMC. The nickel cobalt aluminum, NCA. Then LFP, lithium iron phosphate. There are 4 types of battery, yes, and today. Another battery is fastly emerging like a solid polymer electrolyte battery. They're slowly emerging. And some more, 2 more things. Lithium is emerging. So, yes, and today, there's 4 types of lithium, and lead acid is widely used everywhere. Now, let's go how the lead acid construction and lithium construction bit differing with each other. In lead acid, we are having the 2 types of battery. One is a flat plate battery, another is a tubular battery. In a flat plate battery, we are basically putting more number of plates and increasing the surface area. When we are increasing surface area of the plate, the battery is giving more power. It is like for starting a car, you need a very high power. That's why you are going for flat plate battery. It is like a VRLA battery, flat plate battery. The flat plate battery gives more power. Whereas the tubular battery, the surface area is low, the active material is stored in some kind of, a tube. That's called tubular battery. This gives more energy. This is for lead acid. Whereas for lithium, it is generally, it's a thin foil. Though it is having a different, prismatic type, cylindrical type, pouch type, the fundamental unit is it's a thin foil. When it is a thin foil, the surface area is smooth. When surface area is smooth, it provides very high power. That means generally, the lithium battery will give more power and lead acid battery will give more energy. Now, how this construction really plays in the field with respect to performance. Now, if you really see, in a battery, when we say there's a voltage, the voltage is basically the difference between the positive and negative electrode. This depends on the material quality, not material quantity. It's material and not the amount. There's a voltage. That means whether you are having 1 kg material or 1 milligram material or 1000 kg material, voltage is the same for the battery. Whereas capacity depends on the amount of energy. Higher the amount, higher the capacity. So the energy means voltage into capacity. E equal to V into AH, that's called watt hour. And power is V into A, voltage into ampere. Ampere depends on surface area. That means lead acid, higher the amount and more energy, long duration, mainly for solar off-grid application. And lithium ion, higher the surface area, high power for short duration, solar on-grid application. That's why today in a lot of Western countries, lithium is very famous, mainly for solar on-grid application. When it comes to solar off-grid application, tubular lead acid plays a very, very big role and very, very critical role. Now, what are the requirements in solar off-grid application? In the solar off-grid application, every day, the battery has to deliver 20% of its capacity. Say, for example, if you install a 200 Ah battery for a residential solar, every day the battery should deliver 40 Ah from the battery. Then battery has to work through summer and winter session. Not only summer and winter session, it has to work for minimum 10 years. That means 10 winter, 10 summer. And battery maintenance shall be very minimum. And battery has to deliver required energy for a minimum 10 to 20 years life. And after life is over, how are you disposing the battery? You cannot just throw the battery out. The battery you should be able to recycle it. When you're recycling it, it's basically you're not taxing the environment. It's a recircular economy. More than that, the battery has to be manufactured locally. Say, for example, suppose Africa says, no, I need to import battery from China or India from UK or USA. It doesn't make any sense. The battery has to be locally manufactured. By local manufacturing, you are creating more jobs to the local people. Now, for this life of the battery, IEC, International Electrotechnical Commission, they brought a life cycle test. The life cycle test is called IEC 61427. It's 2005 and 2013 it is modified. Of course, 2014 is the Indian version. Let us talk about the IEC version. Now this standard, what it says, it gives a protocol where it generates summer and winter condition in a test lab. That means in a windy season, first you are discharging the battery and you are discharge between 10 to 40% SOC. 10 to 40% SOC, you are charge discharging and it is for 49 cycles. Then you are charging the battery to create a sunny environment. There you discharge the battery between 75 to 100 SOC for 99 cycle, total 148 cycle. The 148 cycle corresponds to 1 year life. If you do this for 148 cycle in the laboratory, the field it is corresponding to 1 year life. Like that, when they do the thing, in 2005, the IEC standard, the standard brought only lead acid and nickel cadmium, and the standard says the number of units should be declared by manufacturer. It is as per manufacturing instruction, the number of batteries should do, number of units has to be declared. So normally, the battery gives 10 to 20 units. So all the manufacturer will say, my battery will give between 10 to 20 units. Whereas in 2013, in the modified version, they brought lithium into picture and they made it 3 units. That means the IEC standard itself shows lithium battery will not give more than 3 units. Whereas in 2005 version, it is the manufacturer has to declare, the manufacturer is declaring 10 to 20 units. Today you take any leading factory catalog, they'll be declaring 10 to 20 units. Whereas here the standard says only 3 units is sufficient. So this itself will give a very clear idea as well for the solar off-grid application, tubular lead acid is preferable. The next slide, this is typically what Eastman we are going to provide. This is our Eastman tubular lead acid battery. One is 220 AH, another is 150 AH, and each is called 1 unit. Now, if you really look at it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, already 11 unit is over. Still, battery is running. So the Eastman battery can easily cross 15 units. That means 15 years life, design life in the field. So this is what Eastman is offering to South African market. So this slide shows how this 1 unit is 1 year. I think this is a little bit, some kind of a mathematical, not say mathematical, some kind of, if anybody interested, we can go through it, or I'm leaving this to, along with the presentation. If anybody interested, they can take this and they can go through it, how this 1 unit corresponds to 1 year life. Okay, 20 units means 20 years life for lead acid. 3 unit means 3 years design life for lithium battery. A lead acid battery can deliver 1,650 times of rated capacity in solar application. Say for example, in residential purpose, if you are installing 200 Ah battery, this will give 200 into 1,650, that much amount of energy in its lifetime. This is a design lifetime of lead acid battery. That means till now it's very clear the lead acid in terms of life can give nearly 10 to 50 years. The next is not only giving life. How do I know whether the battery is fully charged or not charged? A simple measurement of specific gravity, a simple measurement of OCV is enough to show whether the battery is 50% or 40% or 30% or 100% SOC. This is a simple graph. This is possible from lead acid battery. A simple measurement of a specific gravity versus SOC or OCV SOC will give you what is SOC. Say for example, when I measure specific gravity is 1.23, I'll say it's my 80% SOC. If my specific gravity is 1.19, I say it's 20% SOC. If my voltage is 12.4, I can say what is my SOC. So a measurement of SOC is very simple in lead acid battery. So this is a great advantage in the field. In the case of lithium metal oxide or NMC, also it's very easy. Simply by measuring voltage, we can see what is SOC. It's very, very easy in NMC. But in NMC, the only one reason it is not safe. The reason being, this is some kind of an hardcore mathematics, hardcore chemistry. Just I will try to explain you. Say for example, in NMC we are using cobalt and nickel and manganese. In cobalt, in NMC it is in the form of CO3 plus and CO4 plus. When you do the electronic configuration of CO3 plus and nickel and manganese, CO3 cobalt is in charged state is unstable because there's one free electron is there. Whereas in the discharge state is more stable. Whereas nickel in discharge state is unstable, in the charge state it is more stable. Same thing manganese. In discharge state is unstable, charge is more stable. That's why in the NMC we do a lot of combination to make it more and more stable. But in practice, whenever we do the overcharging, these NMC batteries are prone for fire, which you might have seen or you might have read in several recent, the newspaper publications. LFP is much more safe than NMC because we talked about lead acid, then NMC, lithium, and LFP. LFP is more safe, but problem is in LFP, the SOC monitoring is very difficult because the voltage versus SOC, the curve is very, very flat. Because of this flat curve, and also it gives hysteresis. Whether you in the charge state, it gives one voltage, in discharge state, it gives other voltage. So this is very, very difficult to predict SOC of a LFP battery. For that, we need a lot of BMS. The BMS involves a lot of mathematics that really it gives more and more cost. Because when you go for BMS, you have to bring all this mathematical like Coulombic method, neural methodology, impedance methodology, fuzzy logic method, Kalman filter method. Several models are there. Several methodologies should be brought. That means basically it increases the cost of a product. A common man cannot afford to do all these things. Another thing when we go for lithium, the problem is when you do the charging, okay, the safety is very, very important. Because in lead acid battery, you can overcharge the battery. By overcharging, the cell dissimilarity you can overcome. See, if we are making the battery 1,000 battery per day or 10,000 batteries per day, we cannot make all the battery same level. There is some kind of variations will be there. That variation is addressed by overcharging in lead acid. Whereas in lithium, we cannot overcharge. The moment we overcharge the battery, in the case of NMC, the oxygen will evolve, it leads to fire. In the case of LFP, there's a lot of variation takes place. This we need to take care as far as the cost is concerned. And this is a simple methodology, how difficult it is to make lithium battery in third world countries. Say, for example, a typical 85 kilowatt hour battery from Tesla, there's a 7,104 cells are there. In 7,104 cells, 74 cells in parallel, 6 modules, and 16 like that are in series. Now, what to do? Each module, there is a battery management system. It's a slave battery management, and all the 16 BMS is controlled by a master BMS. That's called battery management system. Here, battery monitoring system. There are 60 battery monitoring system. It monitors voltage, current, and temperature. And all this is gone to the major one. There, the centralized unit. It's a central battery monitoring system. So that will monitor all the battery and manage it. So these are two complications which really increases the cost of a battery. Here I compare. In a typical Indian condition, for a residential solar application, between lead and lithium, it's a 1 kilowatt, basically 4 kilowatt hour per day. Then I've taken the Indian unit, electricity cost, Indian rupees, 6 rupees per unit. What is the total cost? 8,760. What is the total solar system cost? And how many number of batteries we need? We need 12 volt, 158, 6 numbers. Otherwise, 690 numbers, 3.0 volt, 2 volt, 5Ah lithium iron phosphate battery. We didn't go for NMC because of safety reason. We went for LFP because of safety reasons. And the battery cost for lead acid is 48,000. Battery cost for lithium is 120,000. When we get the breakup, in lead acid we are getting in 5 years. Whereas lithium, it takes 17 years. And in the lead acid, after 5 years, when you are selling the battery back, the people are taking the battery, paying 25 to 30% money. The lithium disposal is a major issue. That means what it says for solar off-grid application. I'm repeating, for solar off-grid application, lead acid, tubular lead acid is much more cost competitive and it is much more value for money than lithium system. More than that, in lead acid, we can have a local manufacturing. We can use a local material. The technology is suitable, whether to India or Africa, anywhere technology is suitable. And material shall be 100% recyclable. Already several African continents that are getting recycled. And it is cheap. Compared to lithium, it is 2 to 3 times cheap. And the product is suitable to local ecosystem like a high temperature system, cold climate, hot climate, tropical climate, any climate lead acid is suitable. And of course, it provides more job opportunity when you go for a solar. With this, I'm concluding. The 21st century is a golden era with prosperity blossoming across the globe. South Africa is on today consuming around, Africa consuming around 840 units. What is the total number of units? I forgot, 1 second. Yeah, 140 to 205 units. African continent has to go up, at least minimum, they have to consume 1,000 units. That means they have to increase 5 times of electrical energy consumption as of now. That means their standard of living is going to increase minimum 5 times. For that, Africa needs to harvest on solar energy. And for solar energy, battery plays a very, very critical role. And the battery plays very, very critical role. Lead acid battery is a local product. And residential solar and rural electrification definitely is going to solve African energy crisis problem. Tubular lead acid is going to play a very, very huge role. So with this, I think probably with solar energy and tubular lead acid, Africa can solve their energy crisis. So thank you very much. So if there is any more questions, I'm willing to answer.
Thank you very much, Dr. Sugumaran, for a very comprehensive presentation, both about technology, but also about the situation in Africa and what the challenges and opportunities about storage represent clearly in the current context. Maybe you can stop sharing your screen so we can see you as questions to ask you. This presentation. First of all, a comment. I really liked your approach of presenting the relationship between more electricity means more better life. I think it's very important. People experience it here in Africa, of course, but you've been able to put some numbers, some tangible elements on the comparison with other countries, and these differences were quite staggering. So I thought that was a very important element to share. And yes, of course, we all want to improve our life standards here on the continent. So definitely we are supporting the further development of solar and the accompanying storage technologies. First question maybe to you. I understood from your presentation that lithium provides more power and lead acid more energy. Those are concepts that we hear of, but if we are not experts, sometimes it's difficult to make the difference between power and energy. Could you please briefly explain again this relationship and what this means for the two technologies?
Yeah, the main difference from a layman terms, it is like a difference between a marathon runner and a sprinter. Both of them are runners. A marathon runner very slowly runs, whereas a sprinter runs at 100 kilometers. That means the difference between energy and power is there is an energy. How fast you are removing the energy? There is energy per time is the power. That means in the lithium, if you really look at the lithium battery construction, basically it's a thin foil and more number of foils makes one battery. Literally the surface area is small. When surface area is small, more amount of material is reacting per second. It is not the amount. Per second, more amount of material. But you are not storing more amount of material. You are storing less, widely distributed. So immediately it reacts. So it gives more power. Whereas in lead acid, what happening? You are reducing the surface area. You are putting more material inside the material, inside a tube. So it slowly it gives energy. It is like you are spending 1 crore in a single day. There is 1 crore you are spending in 100 days. That's the difference between power and energy.
Thank you very much for this clarification. My next question is also about specifics of your presentation. In one slide, you explained that the requirements for battery is to be able to deliver 20% of its energy on a daily basis. And this might be a bit confusing for people who are used to be talked about in terms of depth of discharge. Generally, like the depth of discharge would be much higher than 20%. So could you please explain this number again and how people should understand this?
Yeah, in solar application, see, when you talk about a battery, we say the battery energy should be reserved for minimum 3 to 4 days additional. Because suddenly solar 1 day may come, 2 days may not come. So the battery should be able to deliver the energy. That means from the battery design point of view, suppose a person is consuming X amount of energy, battery should be designed for 5x. So that's a reserve power. So that's why when you design for 5x, when you remove x, it is 20%. Suppose today a person needs a 4 watt-hour per day. Just if a battery also gives 4 watt-hour per day, one day it is over. Tomorrow there is no sunshine. Day after tomorrow, no sunshine. What are you going to do? So you need to have minimum 4 to 5 days reserve power. That's why we are giving an additional 80% extra so that the record amount is only 20%. So in a solar design itself, solar off-grid, I'm taking solar off-grid. The discharge capacity is 100 means battery will be 500.
This is a fundamentally different reference point
from electric vehicle. Yeah.
Lithium manufacturers,
yes.
Where depth of discharge is significantly higher.
Yes. Even lithium they can't do because the question is, I need only 20 for 5 days. I need 20 for 5 days. That means I need to go for 100. Lithium guys will say, no, I can give 20. Okay, 20 is good, very good enough. Tomorrow, what happened? There's no power. What should I do? So you have to give a reserve. So both in lithium and lead, the reserve, additional reserve 80% should be given.
Understood. You also took some time to insist on the importance of BMS in the case of lithium. Now, there was no discussion about BMS for lead acid. Can you please explain again why this doesn't need to be the case and why this needs to be the case for lithium?
Yeah, see, in the case of lead acid, during manufacturing of battery, they are making 1,000 batteries per day, or some factory 10,000 batteries per day. All the 10,000 will not be same level. There is a manufacturing tolerances out there. The battery capacity may vary. If it's a 100 Ah battery, it may be 101, 102, 98, that kind of variations. It is there both in lead acid and as well as in lithium. But in the case of lead acid, we overcome by overcharging. Whereas in lithium, you can't overcharge it. See, lithium, the moment you overcharge it, in the case of NMC, you are prone for fire. In the case of LFP, more and more variations started. Whereas in the case of lead acid, you can overcharge it. By overcharging it, you are losing only water. You are not losing the performance. So the water loss can be mitigated by putting, automatic water tapping. Since overcharge is possible in lead acid, overcharge is not possible in lithium, you need to have a battery management system. That's a primary criteria for it.
That is very clear and understood. Thank you very much.
Thank you, yes.
Many people listening to us today, and rightly so, they are, of course, interested in costs. And in some part of your presentation, you highlighted quite a steep price difference between lead acid and lithium. Now, to play a little bit devil's advocate, even though things may have slightly evolved in recent time, the general trend for lithium is to get cheaper and cheaper in a similar way as solar panels have gotten cheaper over the last 10-15 years. What can you say about the price evolution on the lead acid side? Is there also some evolution, or is it almost flattened out? What should people expect for the near future?
See, the lead acid side, the price is almost flattened. Now people are looking for higher life battery. When they go for higher life battery, there's a lot of research is going on. When higher life battery comes, automatically the lead requirement will come down. Suppose today, the life of battery is 1 year. You are having certain amount of lead. The same battery, if you increase to 2 years, you can produce double the amount of lead, double the amount of battery. That means the price automatically will come down. One. The second, whenever people compare lithium and lead battery price, they don't take the resale value. Today, as far as the lead is concerned, after usage, the used battery is some kind of a gold mine. People come and take the battery by paying you money. Whereas for lithium, for disposal, you have to pay money. So that price, nobody, in fact, I checked several, cost comparison, starting from leading labs in the world. They don't take this into picture. The resale value. Lead has got a resale value of 25 to 30% of original value. For lithium, you have to pay for disposal. So this value is not considered. Another thing, lead is recyclable. When there's a recyclable, say for example, for original equipment manufacturer or original battery manufacturer, when he is having a recycled lead, he is getting lead cheaper. So his BOM is cheaper. But lithium it is not, because you are getting from fresh material. So the cost goes up. So in the case of lead, the price still can come down. Whereas in the case of lithium, unless a proper recyclable technology comes, which I am not seeing maybe another 10 or 15 years, will be widely used. Okay, maybe 1 or 2 across the globe, maybe there in a little amount, not very wide. So lithium price will go up. Lead acid, there's a chance it may come.
Thank you very much. It's clear that there are some very strong arguments for lead acid as well. Maybe my last question to you today. I'm sure many listeners here today have learned a lot about the advantages of this technology. And let's imagine they want to engage in a solar project with storage. Most of the end users are not experts in storage technologies or even the different kinds of panels that are out there. They are generally trusting the local installer for that technical choice. What would be your advice for an end user to try to influence or to make sure that they are making the right technological choice for their projects? What should they be looking out for? What should they be requesting from their solar installer?
It's a very, very good question. I think across the globe, this is a major problem. In fact, most of the people are, swayed by the salesman. The salesman goes and tells something and people simply buy it. But nowadays, people are a little bit, more aware about this internet, the fire incidents everywhere. I think people should really look for safety first, then recyclability and cost. Safety, recyclability, cost, and of course, performance is very, very important. Performance, there's no compromise. Apart from performance, these three, when people talk and try to get the information from, the guy who is coming and trying to advise, this is the best and this is the best, just ask him, is it safe? Just ask him, is it recyclable? Just ask him, is it previously used? Show some history, tell them the cost. These are the things. I think this basically, even the local government also should help. Local government and the manufacturer, that's everybody should help and educate the people. So this is my suggestion. Beyond that, I can't give any suggestion for this.
Well, this is a great conclusion of our session today. Thank you so much for sharing all these insights and the results of your many years of research on the topic. It's been great having you, and I wish you a wonderful rest of the day.
Well, thank you very much. In fact, our Eastman company is selling a lot of this tubular battery. If anybody interested, they can talk to Eastman guys and they will help you also.